Welcome to this video, the final video in my series of videos on Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 20 is titled The Epsilon Numbers of the Second Number Class. This is a fairly straightforward section. The proofs of the theorems are fairly complete already in comparison to some of the previous sections where there's been a lot of detail missed out. Suppose we have a number alpha as given in point 1 of page 195, and such that the degree of alpha is greater than alpha. That is, alpha naught is greater than alpha. Then alpha is equal to omega to the power of alpha naught times kappa naught, plus omega to the power of alpha 1 times kappa 1, plus and so on, which is greater than or equal to omega to the power of alpha naught by theorem C of section 19. But omega to the power of alpha naught is greater than or equal to alpha naught by theorem F of section 18. And so, omega to the power of alpha naught is greater than alpha, which is a contradiction, since we effectively have that alpha is greater than alpha. Therefore, the degree of alpha can never exceed alpha. Now suppose alpha equal to its own degree, that is, alpha equals alpha naught. Using the notation of expression 1 of page 195, then the expression in 1 becomes alpha equals omega to the power of alpha times kappa naught, plus omega to the power of alpha 1 times kappa 1, and so on. Now suppose this does not reduce to omega to the power of alpha. Then alpha, which is equal to omega to the power of alpha times kappa naught, plus omega to the power of alpha 1 times kappa 1, and so on, is greater than omega to the power of alpha by theorem C of section 19. This contradicts theorem F of section 18. Of course, we don't actually know yet whether there exist any numbers which are equal to their own degree. That is, we don't know if there are actually any epsilon numbers in the second number class. However, theorem A states that any number of the first or second number class that is not an epsilon number, which are not exactly hard to find, can be used to find an epsilon number by using the process indicated. Thus, theorem A also confirms the existence of at least one epsilon number. Note that if gamma is already an epsilon number, then each of the numbers gamma 1, gamma 2, and so on would all be equal to gamma. In the proof of theorem A, note that none of the numbers gamma 1, gamma 2, and so on are epsilon numbers, since we see that omega to the power of gamma is greater than gamma, therefore gamma 1 is greater than gamma, and so omega to the power of gamma 1 is greater than omega to the power of gamma by theorem B of section 18. Therefore, omega to the power of gamma 1 is greater than omega to the power of gamma, which equals gamma 1, and so gamma 2 is greater than gamma 1, and so omega to the power of gamma 2 is greater than omega to the power of gamma 1, again by theorem B of section 18. Therefore, omega to the power of gamma 2 is greater than omega to the power of gamma 1, which equals gamma 2, and so on. The proofs of theorems A and B present no real difficulties. However, there is a small typographical error on page 196 which is shown on the screen now. For the proof of theorem C, from epsilon primed less than gamma less than epsilon double primed, it follows from theorem B of section 18 that omega to the power of epsilon primed is less than omega to the power of gamma, which is less than omega to the power of epsilon double primed. Theorem C and its proof are straightforward. That all epsilon numbers are of the second kind can be seen from their representation in product form. If xi is an epsilon number, then xi equals omega to the power of xi, which, by theorem H of section 19, is the form of a number of the second kind. Theorem D follows immediately from theorem C. Note that theorem E does not require the sequence of epsilon numbers to be consecutive epsilon numbers, but simply an arbitrary increasing sequence of epsilon numbers. Some of the steps of the proof of theorem E are justified as shown on the screen. The limit of epsilon nu has already been shown to be an epsilon number. However, since the limit of a fundamental series is the ordinal number which is next in order of magnitude to all of the terms of the series, then it follows that the limit of epsilon nu is the ordinal number which is next in order of magnitude to all of the epsilon nu. And since this limit is an epsilon number, then the limit of epsilon nu is the epsilon number which is next in order of magnitude to all of the epsilon nu. In the proof of theorem F, uppercase omega is the type of only the aggregate of the numbers of the second number class in their order of magnitude. Therefore, lowercase omega plus uppercase omega is, by section 14, the type of the union aggregate of the first number class and the second number class. Some of the details are shown on the screen. The cardinal number of the second number class is Aleph 1 by theorem F of section 16. As was explained at the very start of this section, the degree alpha naught of a number alpha is never greater than alpha. That is, alpha naught is less than or equal to alpha. The numbers which are equal to their degree are, by definition, the epsilon numbers. On this page, the proof that alpha times epsilon is equal to epsilon is explained as shown on the screen. In the proof of Theorem G, there are several typographical errors. The corrections of these typographical errors are shown on the screen, and the explanation is as shown. In the statement of Theorem H, note that alpha to the power of xi equals xi does not immediately mean that xi is an epsilon number. Epsilon numbers are defined as those numbers which are equal to their degree, that is, those numbers for which omega to the power of xi equals xi. Even though it's deduced at the very start of the proof of Theorem H that beta is greater than alpha, it still needs to be shown that beta must also be an epsilon number. The justification that b is greater than alpha is shown on the screen. The claim that alpha to the power of beta is greater than beta in the case that beta is a number of the first kind is shown on the screen. The correction of a typographical error is shown on the screen now, and since alpha to the power of beta is equal to beta, by assumption then it follows that omega to the power of alpha naught times beta is equal to beta. By Theorem H of section 14, beta is less than or equal to alpha naught times beta, and so, since it has been shown on this page that we also have beta is greater than or equal to alpha naught times beta, then we must in fact have that beta is equal to alpha naught times beta. From here the result follows. Thank you for watching this video. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.